Welcome again, everyone. Another episode of Disruption Drives. I have with me Florian Rohde today. Florian is the co-founder of iProcess Consulting, an engineering consulting firm focused on the future of mobility, autonomous vehicles, and software-defined vehicles. With a prior background that includes distinguished stints at Continental, Tesla, and Nio, I reached out to Florian to share some of his insights based on his deep knowledge of the entire vehicle autonomy suite, electrification, and battery technology. I can think of no one better to help us navigate this world of software-defined vehicles and the autonomous suite than Florian. So thank you, Florian. Thank you for joining us.
Hello, yeah, thanks for having me and good morning, good afternoon.
So Florian, let me start with asking you, right? What does an autonomous broadly in any vehicle, what does that suite consist of? What does an autonomous vehicle technology stack look like?
So I think the first thing I wanted to mention it's a difference between an AV, so autonomous vehicle, and an SDV, a software-defined vehicle.
We'll
A lot
talk
of
about SDVs broadly, but what does that
uh-huh.
thing? Yeah.
So in general, people are sometimes throwing this together. This is why I wanted to make this statement first, right? So there are autonomous vehicle platforms out there right now that are not software-defined vehicles, and there are software-defined vehicle approaches out there that are not autonomous vehicles. But when you look at the stack of an autonomous vehicle, it is very easy to use this to explain the idea of software-defined vehicles. So you have a hardware component, a sensor suite, and depending on which approach you are following, you have radars, lidars, you have ultrasonic sensors, and you have cameras. And that is also amended with what is called high resolution maps and also real-time information, maybe from vehicle to vehicle or vehicle to environment communication. So you see, it's very complex, and I could go more into detail there, but I think the main point is it's very complex, and these complex things have to work together. First of all, to try to see, quote unquote, the environment. So this is where is what is called sensor fusion comes into play. So the car has all these different ways, similar as you as a human, right? So you have a couple of cameras, you have a couple of radars, and you have a couple of other sensors you can use, and your brain is actually creating your environment out of this. So the autonomous stack is doing the same thing, what is called a sensor fusion. They bring all these things together, and this is going then to what is called a perception. The perception actually builds a model, a digital model for the car of its surroundings. And then from this perception, you go into decision making, path planning, and then vehicle controls that actually, in the end, actuates the steering, the acceleration, the deceleration, turn indicators, all this kind of things. So all of this together is a very complex, as you can hear it, as a very complex system. And this very complex system has to work together in a way that is different than cars used to be working all the way up to the 2000s, where you had different computers, little computers doing their little thing. You know, you had a little computer to roll your windows up and down, you had
Right.
a little computer to turn your lights on and off, but they were never interacting with each other, right?
Absolutely.
Now you look at the AV stack, this is why I love the word complex integration, right? Or the two words, because these things have to work together. So my camera has to provide information, my lidar has to provide information. This has to be taken together, including what does the driver do if I, for example, I have an L2 or L3 system, right, which is not fully autonomous. All these things have to be taken together in a compute and actually have to make decisions. And on top of that, it has to be safe. That's the
Absolutely.
most important thing.
And let's talk a bit. Let's me talk about the sensor suite in specific. Because look, well, again, going back to the commercialization angle here, how dependent is the various sensor suite to the external environment? Particularly, look, there's a general thesis out there that the weather, quality of the road's infrastructure, density of the environment itself matter. So talk to me a little bit about that. Is that problem solved, or is that still a limitation on a sensor suite?
So I personally, I'm a proponent of saying level 5 is not possible. It has to be level 4, and we are growing ODDs, operational design domains, for that very reason. So by definition of SAE, level 5 means that you have a vehicle that can handle any situation anywhere in the world limited to this planet for now. But I can guarantee you, I find you an operational design domain somewhere that it doesn't matter how mature your stack is, you cannot handle. Same as you and me as a human, right? If I put you down into the Amazon and let you drive like a jeep through the bush, you would probably struggle as well. So that being said, there's two ends of the spectrum, right? So there's like, hey, I want to keep it simple, aka affordable and cheap, but that limits me strongly in my operational domain. So, and there are good examples why you need that. For example, people movers going fairly slow, like 30 miles an hour in very controlled environment. I can go with a relatively simple sensor suite and a relatively simple approach here. If I want to go highway speed with personal vehicles in a variety of weather conditions, things change. And then your sensor suite becomes much more complex, but also much more expensive. As of today, we are looking at nice weather on good environment with relatively moderate traffic. It's fairly straightforward to build a stack and a system that works well and safe. But lighting conditions are getting very tricky, especially, you as a human, you can see in the night and you can see in the day. And in the middle, there's something called twilight.
Right.
And this is really tricky. And nature had some great ideas how to make our eyes capable of doing that. That is one challenge, right? When you go into twilight or when you have like very low sun going right into your camera and you get glare. Right. So the way you do that as a human, you flap down your little sun visor or you put on sunglasses, right? But your car cannot really do that. So there's a lot of challenges there. And then the other thing, of course, is extreme weather conditions. And it's really tricky for cameras, for example, to see in snow or in strong rain, which actually is not that different for the camera. And then you have all of this different scenarios that come with different challenges. And on the other hand, we've also seen approaches where like putting more and more and more sensors to get more redundancy. Apple SPG had once, there were some pictures out of this like super overloaded vehicle. That is also not a good solution because then it becomes so complex that you have basically too many cooks in the kitchen.
So tell me a little bit about, let's say having too many sensors as well, right? And is there a I guess constraint of physics that needs to meet? What happens? Because look, one of the well, you're basically hitting the point, which is that look, you can have a very cheap sensor set that is that's focused on one environment, probably one use case, industrial, maybe like a single target zone, back and forth all together, and that's fairly easy to build. On the other hand, if you have basically loaded up with sensors, it could be technically level 5 as long as you build every sensor humanly imaginable. What are then? And there's various different modes of sensors. What is the comparison of them? There's at least radar, lidar, lidar, cameras, and ultrasonic.
Yeah, and there are different opinions out there, right? So there are companies who are going full LiDAR, and there are companies who are going not even radar. And without naming them, you know who I'm talking about. So the approach is it's a little tricky because the CEO of that company says, I only have 2 cameras, which I'm using to move around as well as a human. The difference is, as I already mentioned, is like the light dependency we can handle as a human, but also the focus, right? Our cameras have analog focus. You can focus like far, near, and really fast, right? So that's getting tricky, and that's where you bring in the sensor fusion, also, next to the weather situations and so on. So different sensors have different pros and cons, right? Cameras are great, for example, to read markings on the road or traffic signs. Radars can't do that. LiDARs can't do that, right? Cameras are great in sunshine or in nice weather. LiDARs are better in bad weather or in the night. Radars are good in long distance ranging or in mixed distance ranging, right? So there seems to be a sweet spot how to equip a car these days. And if you look at the Zoox car and at the Waymo car, they basically have similar sensor suites on them, right? Okay. So there is an agreement in the industry how you actually sense. That's
And
the
what is that? What is that sort of at least at this point configuration?
So right now you have corner lidars, corner radars, you have long distance radars, you have something that looks into the back and into the lanes that can be camera based, right? Um, and all this information coming then fused together. Um, it's how to say it's a little different from approach to approach, but outside of Tesla, the consensus is that you need lidar for bad visibility
Bad
situation.
visibility situations, right?
Yes,
Fair enough.
exactly.
Fair enough. One of the things you mentioned was, look, let's talk a bit about the types of, I mean, there's delivery versus passenger type vehicles.
Hmm.
Broadly, there's many others, industrial automation and so on. Let's include that in.
Yeah,
How is
and
how is that? What are the considerations different technically?
this actually pairs up nicely with the statements we had before about the use cases. So you have different use cases from speed point of view, as I mentioned earlier. It's very different. If you want to go only like 25 miles per hour, you can calculate how much you travel per second and what kind of like reaction rate you need, right? But if you want to have something that goes highway speed, which can be in some states like 85 miles an hour, you have to be so much more equipped to look far, and that's getting really tricky. And that's for the transport of people in passenger cars. I think one of the biggest challenge is the mixed controls. So you have human controls and you have automated controls, both in the same vehicle, but also in the same flow of traffic, right? So you have automated vehicles, or you will have at one point automated vehicles, and you have human-driven vehicles together, right? If we would, from today to tomorrow, remove all humans from driving, which you can't, but it would be much easier to automate that, right? Because you don't have all these unknowns, right?
You don't have
And
the
that,
rational exuberance.
yes, and then on the other hand, you also have a variety of transportation of goods, which starts in the warehouse, for example. Very different use case. I don't want to say it's easier to automate, but it's a simpler environment you can handle, and you control the environment. That's a huge
What
thing.
about things like dust? I mean, like mining locations sometimes have autonomous vehicles, and
Super interesting. Yes, very different, very different challenges. Exactly. So they suddenly have to put in like washing features for their cameras, which you usually, you do it on a highway vehicle. Yes, you wash it when you wash your windshield, which is roughly enough, right? But for the mining stuff, you have very different environmental factors, and you have to take these into consideration. But it's interesting that in mining, they're running fully autonomous for a decade or more, right? Because they control the environment and they own the environment.
right.
And the other thing is, if you're doing transportation of goods on private ground, like for example on a mining truck, to come for a full stop in case of a doubtful situation is usually a safe scenario.
Yeah.
If you go down 80 miles an hour on the interstate, to come to a full stop is not a safe situation, right? So very different. And then you also have what I mentioned earlier, the people movers, right? So people movers, very different because there's no driver. There's no consideration for a driver. There's no driving area. They have a safety supervisor, which has a emergency button, but the vehicle does not have to be designed to be driven by a human. Gives you much more freedom and flexibility in designing your autonomous vehicle rather than have the clunky steering wheel and the steering rack and pedals and all this kind of stuff where humans can actively or mistakenly interact with the vehicle.
I see your point. That's a good segue into actually one of the things I wanted to ask you, which is you mentioned there's of course there's vehicles that are designed to be autonomous, and what the term that's being used, of course, you know this, you speak this language every day, is software-defined vehicles. Traditionally, when we think software, we don't think of the car itself as a piece of software. Today, that's changed. So what parts of a vehicle, of a software, what is a software-defined vehicle? What is software there? What still remains hardware?
So It's interesting. If you ask 5 people, you probably get 7 different definitions of what a software-defined vehicle
Two
is.
people are going to cheat. Okay, fair enough. All right, fair enough. Go ahead.
But in general, I try the layman's terms. So if I would explain it to my friends and family, you know, back in the original days of EE architecture, you had different components in the car responsible for different parts, similar to your desktop tower you had like 20 years ago in your dorm room, right? You had a hard drive and you had a graphics chip and whatever. Now we are both looking into a laptop, and I cannot tell you if I have a graphics chip in there or not. And I don't care, right? Because there is a generic hardware platform which is capable to provide features through the software that runs on it. One feature is, for example, to put you on my screen, right? And if that runs through a coprocessor or so the main processor, I don't care, right? So eventually, the software-defined vehicle idea is that you have the car as a compute platform that can provide features to the user, independent of what hardware is in there. I mean, for me as a user, independent, right? So there might be a central compute system, or there might be a multiple high-power compute systems. This is all in flux and discussions right now, how the architecture will look like, because there are pros and cons for everything. But the main idea is you don't have hardware components that are, with the support of embedded software, providing specific functionalities to a specific use case or a specific
Tell me
need.
about this, right? Because there's the car and the very foundational need for a car, which is just it's moving.
That actually it gets amended with a lot of more functionality, and that's why, for example, in Chinese market, SDVs are much more progressing, because cars are not moving a lot there. They're standing usually in a traffic jam, right? So their main focus on the car is it has to entertain, it has to act as an office, it has to provide information, and it has to be a communication central to the outer world. So the moving of the car is actually almost secondary for them.
Interesting. That's really interesting, because now the car is being seen as almost a hospitality market rather than actually a functional transportation market. Like
Correct.
the iPhone changed because it's a collection of apps and what it does rather than
just bringing you from A to B. That's exactly right. So one of the most important features of the SDV generation in China right now is a karaoke system. So people are putting more value on that than on horsepowers. Which
let me ask you this though. Let's at the end of the day, still the horsepower need doesn't go away. But would it be actually feasible for a user to customize their horsepower simply based on software?
Yes. But it's to add on that, it's interesting. So now that we're transitioning to electric vehicles in a lot of markets, horsepower literally is abundant. So, you know, I drive my daily driver vehicle. It has 400 horsepower. That's more than I ever need, right? So it's not that important anymore. Electric cars are much quicker from the horsepower rating or from the power rating.
But there are you can use software to basically decide how much electricity, how much power you need to use for your
correct. But within, of course, the design limitations of the vehicle. Right. But I give you an example. Back in my Tesla days, actually, we launched the Model 3 with a certain horsepower rating. And over time, after we learned more about the durability of the vehicle, we actually released higher levels of horsepower or like power. It's not really horsepower, right? Like kilowatts. Through software updates in different fashions, either as a goodie to the owner, or also as an optional income to the company, right? So you can actually buy upgrade.
You would have to change your battery, and a higher horsepower machine would be a different machine.
So there are two different options. One option, what we actually had it software limited to learn more about the durability, and then we released. So the hardware was already there and designed for it. We just released more power. Another option is what Nio does, for example. They offer you battery pack swaps. And with battery pack swaps, you can actually get different power or different range in the main focus, right? So imagine that. You drive around in a city with a small battery pack, which is lightweight. Your consumption is much better. And then you go once a year, you go on your long drive. So you swap in a much bigger battery. Software supports that because they have to work together. The integration has to work in your car, wherever you go, not in the engineering center, right? And you get much more range. You pay for it for a couple of weeks, like a leasing, and you come back and you get your smaller battery back for the rest of the year.
Interesting. Why is it traditionally considered that a software-defined vehicles is easier to automate entirely. And I assume we would love to hear your thoughts on it because at some level,
Yeah.
yes, the fact that you can write everything on software makes it easier. But does it necessarily make it a safer vehicle on the road?
Okay, that's two questions. So let me answer the first question. So a software-defined vehicle, and there are very, very few out there right now. I still believe Tesla has the best platform for that. There are a few others out there, but software-defined vehicle is in its infancy. And the reason why it makes it so more interesting for continuous development is its flexibility, right? So I can actually do things in a software-defined vehicle I haven't originally designed for this vehicle to happen, right? While in the standard EE embedded architectures, things have been frozen and designed to serve a certain goal, hardware and software. And it's very, very hard to do changes on that afterwards. So that's why SDVs allow for much more ongoing development and more features and so on. The safety aspects is a very, very important one, and I don't want to have anybody forgetting about that. So it's very important. The advantage is that the SDV allows things to be supervised on the vehicle level for safety as well. While before and ongoing, you have supervision of safety in each controller. You can have the vehicle as a whole starting to supervise the behavior. This is nothing we really see out there yet, but once we move on to the architecture of HPC, high performance computers, there are things they call a hypervisor, something like this, that runs independent in your system and supervises the entire vehicle for safety, not only your steering system, for example, or not only for
Software can,
acceleration.
in words, software can keep track of essentially the control processing unit, as you said, will keep track of safety records for the entire vehicle fundamentally.
Yes, both things actually. It will actually supervise the safety in real time in order to if action is needed,
I see.
and also it will keep the records for data analysis later. And in the bad situation of an accident happen, which unfortunately happens from time to time, actually also helps you to really understand what happened.
Absolutely. So we're entering in a world where the car basically is going to be like an iPhone, effectively, right? Or do you
To a certain extent, but with a very important layer of safety added to it. So
right?
that's the important thing. And actually, let me add that. So first of all, obviously, an iPhone doesn't drive your car into a tree. So that's why you need an added layer of safety. But there's another often forgotten, much more not more challenging, but challenging engineering problem, quote unquote, the longevity of the product. iPhones last for 2 to 4 years. I don't know the exact number, but
Well, Apple
some
decides to make it bad after that. Apple, if
yeah,
anything, just
right. But those phones are designed for a relatively short lifetime, and they're living within your pocket and inside your house. Cars are designed to live. I don't remember the latest number, but they're like 12 to 18 years on the market and so on. And they are parked outside, rain or shine, right? They are parked at minus 40 Celsius. They're parked out there at plus 40 Celsius. And they have to survive everything. They have to be capable of, you go out to your car at plus 40 degrees Celsius, which I have here right now in Las Vegas. I go into the car, I turn the key, and I floor the pedal, and I go on the freeway right away.
yeah.
So if you take, and it's not only iPhones, any smart device, any smartphone or laptop, and you open that up at minus 40 degrees Celsius, it will last you minutes, and then the battery will be gone, the screen will be dark, and everything. So this is so much more challenging for cars, and that explains why cars are a little behind the perceived technology than what you see in IoT.
Very fair, very fair. And it's very likely that that's probably one of the reasons why Apple decided to not follow cars and follow the market into cars. But who knows?
I'm not giving you any
I don't know.
any ideas about that.
I
But
don't know,
yeah.
but no, there was once upon a time definitely a rumor that Apple would be the ideal car maker. Maybe I mean, maybe, who knows? They may still get into it. But
Well,
Florian,
they're all at Ford now, so we probably get an Apple
no, because
Ford.
Amazon's
Yeah,
got
yeah.
one, Google's got one. I'm assuming Microsoft and Apple should get something in there, and Uber's already in there. So Uber's become the aggregator.
We'll
So
see.
every one of the cool kids has one, and so they need to. I mean, Microsoft and Apple, it's they need to step up their game now.
I think Apple figured they make much more margin on iPhones than on cars.
Yeah, but when the next record is $10 trillion companies and Apple starts feeling like, outside the Fortune 50, that's not. I'm assuming
Yeah,
they will change their mind. But anyway, that's probably a conversation for a different day.
probably.
Did want to summarize what we talked about. The software-defined vehicles are a little bit behind, but are likely going to be the iPhone of cars. They're soon coming. So wanted to thank Florian Rohde. I know he pronounces it Road in the US and Rohde,
That's right. In
German.
Europe. Yes.
We will
Of
say to that. Florian, again, thank you so much for making the time. Uh,
course.
Software-defined vehicles and the tech stack for autonomous vehicles. If I hope you all have fun, and thank you again, Florian.
Of course. Yeah, I had fun.